Assalamualaikum and good morning to Dr. Fuad and my classmate. It is an honor for me and my group member to be here with you guys in this online class to deliver a presentation. The topic of our presentation from group 4 is UV-VIS spectroscopy. As we know that UV-VIS spectroscopy is one of the important methods for polymer characterization, hopefully the presentation will make you understand more about this topic. In this presentation, we will cover 3 main points. First, introduction. Second, how to characterize. And the last one, example. So that would be the overall structure of our presentation. So stay tuned with us until the end of this presentation. Now, let's move on to the first point. First, I would like to talk about the introduction of this topic. Spectroscopic techniques always complement to each other to investigate molecules in solid, liquid, or gaseous form. There is a lot of instruments available for polymer characterization, such as infrared spectroscopy, Raman spectroscopy, nuclear magnetic resonance spectroscopy, and much more. Back in history, Arnold Beckman, in July 1941, he introduced his DU UV spectrophotometer. This method is based on the absorption of ultraviolet light or visible light by chemical compound, which resulting in distinct spectra. Spectroscopy is based on the interaction between light and matter. UV spectroscopy is one of the important analytical tools for the chemical structure characterization of polymers. Their main function is used to detect chromophores of matter qualitatively and quantitatively, and not to forget, it helps to measuring the extent of their conjugation. The wavelength range for UV spectroscopy is 190 nanometer until 800 nanometer. Common things that you need to know in UV-VIS instrumentation is there are 4 main components in UV-VIS spectroscopy. The 4 main components in UV-VIS spectroscopy is light source, monochromator, sample, and detector. UV-VIS spectrum consider only the absorption of the light by matter, because light is a form of energy, and absorption of light by matter causes the energy content of the molecules or atom to increase. For the peak, when light passes through the compound, energy from the light is used to promote an electron from a bonding or non-bonding orbital into one of the empty anti-bonding orbital, which is the cause of the peak to expose. That's all from me, Izzatul Nurnabila binti Jamil. For the next point, Nurul Azmira will explain more about UV spectroscopy. Thank you.
Now let's move on to characterization of polymer. So this UV visible spectroscopy are able to detect the chromophore. Chromophore is specific conjugated group in the molecule of polymer which can be identified quantitatively and qualitatively. It will absorb electronic transition of bonding orbital level to anti-bonding orbital level, which is n to pi star and pi to pi star transition upon light irradiation. It will identify the impurities in polymers such as residual monomer, inhibitors, antioxidant, etc. But it will not absorb molecule with no double bond or with only one double bond. And the greater the conjugation will give longer wavelength of maximum absorption. Here are some examples of chromophore, which consists of alkene group, carbonyl group, nitrosyl group, and halogen. So the value of any peak in the spectrum of a compound is a constant characteristic of that particular molecular structure. Most of conjugated polymer will exhibit absorption in the visible range, and band intensity can be depends on two factors. Firstly is on the particular molecular structure, and secondly is the number of absorbing molecules in the light path. Now let's look to the upper figure. So we have benzene, and the next one is naphthalene. As you can see, benzene has lower conjugation than the naphthalene. So it is true that stated from the slide before, the greater the conjugation, give longer wavelength of maximum absorption. So the next one is the spectrum, the example of the UV visible spectrum. So in this figure, it shows a typical ultraviolet absorption spectrum of organic compound. It is unlike the infrared spectra. UV visible spectra are quite broad and generally show a small number of peaks. These peaks are reported as the wavelength where maxima occur. The conjugated unsaturated ketone, whose spectrum is shown in this figure, has an intense absorption at lambda max of 232 nanometer and a much weaker absorption at lambda max 330 nanometer. So that is for the spectrum. The band at shorter wavelength will correspond to a pi electron transition. The longer the wavelength, the weaker the intensity of the band to a transition of the non-bonding electrons. The intensity of absorption can be identified quantitatively too by using Beer-Lambert law. So this law consists of a formula of A equal to epsilon Cl. A is stand for absorbance, epsilon is molar absorptivity, C is concentration of solution, which is mole per liter, and L is path length. So here the absorbance is also defined as the log of ratio and light intensities that will enter and leave the sample. Here is the comparison of UV visible spectroscopy and IR spectroscopy. So UV visible spectroscopy will detect electronic transition, as I told you before, and IR spectroscopy will detect vibrational transition, even though both are electromagnetic radiation spectrum. So other than that, UV visible spectroscopy will detect any conjugated pi system present in the compound, while IR spectroscopy will detect the functional group present in the compound. Other than that, the UV visible spectroscopy will show only one or two peaks in the spectrum, but IR spectroscopy will show many peaks of functional groups in the spectrum.
For example of UV visible spectroscopy is first, spectroscopy analysis of polymers, polystyrene LDPE. The diagram shows the UV visible absorption spectrum for polystyrene. Absorbance on the vertical axis is the measure of the amount of light absorbed. The higher the value, the more of a particular wavelength is being absorbed. The absorption peaks at a value of 238 nanometer. This is in the ultraviolet, and so there would be no visible sign of any light being absorbed. So the polystyrene is colorless. The symbol on the graph, lambda max in polystyrene, they are non-bonding electrons. This means that the only electron jumps taking place within the range that the spectrometer can measure are from pi bonding to pi antibonding orbitals. Here is the explanation for the UV visible that I have explained just now. Next, example for UV visible spectroscopy is in biomedical application. Titanium dioxide nanoparticles have the potential to disengage bacteria under the illumination of UV light, as the incorporation of titanium dioxide in polymethyl methacrylate provides excellent antibacterial properties. The photocatalytic activity of titanium dioxide, including successful extermination of bacteria, virus, and fungi, enhance for the particles below 20 nanometer. E. coli can be completely killed under UV illumination on titanium dioxide film after an hour, but on the 0.25 gram per liter nanophase titania to completely exterminate all the E. coli in 10 minutes. Then in cosmetic application, which is preparation of silver and gold nanoparticles suspensions. The obtained suspensions were subject to UV-VIS spectrophotometry analysis. A single beam spectrophotometer connected to a computer loaded with Spectra UV software with 1.0 cm quartz cells was used. The spectra were obtained with the following instrumental parameters as shown in the slide. To characterize suspension of silver nanoparticles by a dark yellow color and exhibit suspension containing the gold particle, which is in UV-VIS spectroscopy result, it is dark violet color. Here is the result of UV-VIS spectroscopy for nanosilver and nanogold suspensions diluted to 20 mg per kg. Lastly, in food application, bioprocess and fermentation monitoring. The application of UV-VIS spectroscopy was evaluated as an inline sensor to monitor changes in color and total phenol concentration during red wine fermentation. The sensor presented by the authors was based on multiple light-emitting diodes, LEDs. According to the authors, these studies confirm that LED sensors can be used to measure the concentration of phenolic compounds in line. The incorporation of a 100 micrometer pipeline flow cells avoid the need for dilution of the sample, making inline measurements possible. The sensor provides inline measurement of the evolution of the total phenolic content and color extraction patterns during red wine fermentation.
Okay, now I initially will be summarizing this whole presentation. Many molecules contain chromophores which will absorb specific wavelength of ultraviolet or visible light. Absorption of UV visible radiation by the polymer leads to transition among electronic energy levels of the macromolecules, in which it leads to the electronic absorption spectrum. Molecules which contain pi electrons or non-bonding electrons, which is n electrons, can be absorbed by the ultraviolet or visible light energy and be excited to a higher antibonding molecular orbitals. The intensity of UV-VIS spectrum can be identified either by qualitative analysis, which is by using spectrum, or by quantitative analysis, which is by using Beer-Lambert law. Using the Beer-Lambert law, the absorption of spectra generated from these samples at given wavelength can be related directly to the concentration of the sample. Now you have reached to the end of this presentation. Thank you everyone for listening.